In this presentation, I'm going to be covering the combined gas law. In a previous presentation, we talked about some early gas laws. We talked about Boyle's law, that was our pressure-volume relationship, and we said that the initial pressure, P1, times the initial volume V1 equals the final pressure P2 times the final volume V2. And now this again was our pressure-volume relationship, and we said that pressure and volume are inversely related. In other words, as volume goes up, pressure goes down, or vice versa. What this led to was this situation mathematically where pressure and volume are multiplied on both sides of the equal sign. After going through Boyle's law, we also talked about Charles's law. Now, Charles's law was our volume-temperature relationship, and in Charles's law, we said that volume and temperature are directly related, and therefore these are divided by one another. As temperature goes up, volume goes up, and this leads to, again, that mathematical situation of division for Charles's law. We also talked about Gay-Lussac's law, very similar to Charles's law. In Gay-Lussac's law, pressure and temperature are directly related, and just like Charles's law, that leads to them being divided in our algebraic equation here. Now, these laws work when only two variables change at a time. But in real life, there are many situations when all three of these variables, pressure, volume, and temperature, all change. So we need a gas law that takes all of these and puts them together so we can make predictions about how these different variables are going to change together. Notice Boyle's law with multiplication, Charles's law with division, and Gay-Lussac's law with division. We're going to put these together where all of these laws are still satisfied. To make this combined gas law, reminder, it's a combination of all our previous gas laws, and it works when pressure, volume, and temperature all change at the same time. But this number of gas has to be constant, the number of gas particles. So we're still dealing with a situation when we're not adding or removing gas. Now, if we use an equation where pressure and volume are multiplied, but pressure is divided by temperature and volume is divided by temperature, we end up with this equation down here, where those same mathematical relationships are all satisfied. Pressure and volume are multiplied, pressure and temperature are divided, and volume and temperature are also divided. Again, this allows us to predict how all three variables will change in a situation where that's possible. One situation you might see in real life where this might happen is tires. Let's say you have a very cold morning, so your tires are cold, it's a low temperature, they have a lower pressure than what's normal, and they're a little bit flat, so they have a slightly lower volume than normal. As the day heats up in the afternoon, the tires get warmer, your temperature goes up, the pressure gets a little bit higher, and the tires inflate a little bit so they don't look as flat, they have a slightly higher volume. Basically, this law is super important when temperature's changing, pressure's changing, and your container, the tire in this case, can change volume. Now, how do we actually do the math for this situation? Well, let's do one practice problem. Now, this problem is going to work very similarly to what we saw in our earlier gas laws. We have a volume of a gas-filled balloon is 30 liters at 313 Kelvin and 1.15 atmospheres of pressure, and we want to know what the final volume will be at STP. Now, STP we talked a little bit ago about. It means standard temperature and pressure, and I'll talk about that once we start setting up our problem. First, let's list everything we know. We know the initial pressure, volume, and temperature as given in the problem. Now, when it comes to STP, that standard temperature and pressure, that's basically just shorthand for saying that the pressure is 1 atmosphere and the temperature is 273 Kelvin. And these are around normal conditions. 273 Kelvin is 0 Celsius, so it's around normal, and pressure is that normal 1 atmosphere that we experience on our daily basis. So when you see STP, that just means your pressure and temperature are these values. I'll plug those in, and because I don't know my final volume, I'll put it down as some question marks, because that's what I'm looking for. Now I'll set up my equation, my combined gas law. I'll plug in those values that I know, leaving V2 as a variable, because I don't know it, I'm trying to solve for it. Now, how we solve for V2 is I'm going to set up an inverse fraction here so that Kelvin, 273 Kelvin, cancels on the right side of the equation. 1 atmosphere cancels on the right side of the equation, so that V2 is left alone. Now, what I do to one side of the equation, I have to do to the other. So I'll again multiply by 273 Kelvin over 1 atmosphere. Notice that some of the units cancel. Kelvin cancels, and atmospheres cancel. And now all I have to do is rewrite my problem to make it a little cleaner. I'll put my numerators multiplied by each other, and my denominators, I kind of nixed the 1 here. 1 times 313 is just 313. And now if I evaluate this math, 273 times 1.5 times 30 divided by 313, I'll find that my final volume is 39.5 liters. So this situation is very similar to our early gas laws, we just have a few more variables. Now let's look at a problem where there's one kind of curveball thrown in, and I'll tell you how to kind of get around it. In our second situation, we have all the conditions given of this gas. Feel free to pause the video to read through this situation. And we're trying to find the final temperature of the gas after pressure and volume change. I'll first list my initial conditions and my final conditions, at least the ones that I know. I'll take them right from the problem. I know the final pressure, I know the final volume, and I'm looking for the final temperature. Again, I'll start with that equation, that combined gas law. I will plug in everything I know from the problem. And notice that in this case, what I'm looking for is in the denominator, my temperature. When this happens, we have to get that variable out of the denominator. It has to end in just the numerator or in a normal spot. Now, my trick for doing this is I like to flip both fractions. Notice the fraction on the left flips, and the fraction on the right also flips. We've basically inverted both fractions. All this does is help us get our final temperature out of the denominator, and it's algebraically allowed. Now the problem is very similar. I'll again multiply by a fraction so that my numbers and units cancel on the right side. What I do to the right side, I have to do to the left. My atmospheres and liters units cancel. I'll clean up my math a little bit, and I'll solve for my final temperature. Now, this is one way to get around a situation when your variable you're looking for is in a denominator, but you can also cross multiplying. If you've learned cross multiplication, it absolutely works in this situation every time. So whether you want to do the problems these way or you want to do it with cross multiplication, either way works. And that is how you do a combined gas law problem.